This is session D6, Photon entanglement, state collapse, and quantum reality. Last session was D5, two spin 1/2 particles. As part of that lecture, we found that two identical, indistinguishable spin 1/2 fermion particles, such as electrons, can only be in quantum states whose total tensor product wave function is antisymmetric for exchange of the two particles. In some cases, the spin state for two fermions can be an entangled state versus a factorizable pure state. However, in the last lecture, we only examined particle pairs that were bound together in space. Today we'll explore photon entanglement, state collapse, and quantum reality. We will learn some surprising and even shocking things about reality in our universe, which has been used to invent uniquely quantum mechanical technologies, such as quantum computing. Don't skip this lecture. We will start by examining the states of pairs of photons, but the results will also apply to matter particles such as electrons, atoms, and crystals. Here's our roadmap. First, we'll do entangled pairs of photons, state collapse, and quantum communication. Then we'll do the state-of-the-art of entanglement. Then the Einstein-Podolsky-Rosen EPR paradox and local realism. Then Bell's inequalities and quantum non-locality. And our final section will be modern quantum technologies, pointing you to online courses for them. This is a possible time to take a break. Entangled pairs of photons, state collapse, and quantum communication. It's possible to generate, source, emit a pair of photons with a definite total quantum state on demand. We can have the two photons travel in different directions and go to different places. We will denote one photon as number 1 and send it to one person, Alice, and the other photon as number 2 and send it to another person, Bob. Alice and Bob will have polarization detectors. The source will be able to, on demand, source a pair of photons of specific tensor product quantum state of polarization. Alice, Bob, and the photon source are at different locations. Let's say that Alice and Bob are each 5 kilometers from the photon source and 10 kilometers from one another. Their locations are stationary, not moving with respect to one another. Their clocks have been synchronized in advance. Alice and Bob know the time at which the source will generate the pair of photons and the time at which their photon will arrive. We will have the photons travel through fiber optic cables, but they could also travel through air or vacuum. We arrange the distances such that photon 1 arrives at Alice a definite short time, say 1 microsecond, before photon 2 arrives at Bob. We don't have to do that, but it will make it easier to go through our arguments, so let's do that. Alice and Bob will each measure the state of their photon as soon as it arrives, but we have arranged it so that Alice always measures hers first and Bob measures his second, immediately after Alice. Something surprising occurs, but we need to build up to it. Photons are spin 1 particles. Spin 1 bosons can have intrinsic spin angular momentum of plus 1 h-bar, 0 h-bar, or minus 1 h-bar, 3 possible values, when measured in any given direction. However, the photon is massless, traveling at the speed of light, and it can only have the two extremal spin values, plus 1 h-bar or minus 1 h-bar, and measured with respect to the axis of propagation. The spin state of the photon is a two-state system, as we saw in lecture D4. We will express the state of the photon in terms of plane polarization, horizontal versus vertical plane polarization, rather than spin or right versus left circular polarizations, because this is more common in courses and articles. We will express the horizontal plane polarization eigenstate of a single photon as h, vertical bar h, angle bracket, so wave function h, and the vertical plane polarization eigenstate of a single photon as v. These eigenstates are orthogonal basis states for the two-state system. The actual state for a single photon might be any superposition, any complex linear combination of the two basis states. The polarization state of the photon will be preserved unchanged by the fiber optic cables or the air medium. Alice and Bob each have a special detector that measures their photon and reports whether the photon was horizontally polarized or was vertically polarized. The detector does not report a continuous polarization angle. The measurement reports either horizontal or vertical. It constitutes a measurement. The detectors are ideal. They never fail to report. They never miss a photon. They never report that the photon was both horizontally and vertically polarized. The detector absorbs the photon. A second measurement of a single photon is never possible. Also, it is impossible to duplicate the photon with an identical state and measure twice. This is called the no-cloning theorem. This is a possible time to take a break. For our first experiment, the source will generate a pair of photons both being horizontally polarized. So the wave function for the total system will be as sourced, and it consists of a tensor product of photon 1 being horizontally polarized and photon 2 being horizontally polarized, which we can abbreviate as state HH. This state for the photon pair is a pure state, being the tensor product of the state for photon 1, H in this case, and the state for photon 2, H in this case. The source clock hits the designated time. The photon pair is generated on demand. Photon 1 travels to Alice, photon 2 travels to Bob. Photon 1 arrives at Alice at the prearranged time. Her detector measures her photon and reports to her that the photon is horizontally polarized. Photon 2 arrives at Bob at the prearranged time. His detector measures his photon and reports to him that the photon is horizontally polarized. No surprise in this case. We could repeat the experiment with other photon pairs sourced in the same state, and we would always get the same result with 100% probability. We could source other photon pairs in other total pure states, vertical, vertical, horizontal, vertical, vertical, horizontal, and we would always get the expected results with 100% probability. This is a possible time to take a break. For our second experiment, we change the source to generate a pair of photons, again in a pure state, but this pure state will be more complicated. It's a pure state. It's the tensor product of a state for photon 1 with a state for photon 2. But the state for photon 1 will be 1 over square root of 2 horizontal plus vertical. And the state for photon 2 will be 1 over square root of 2 horizontal plus vertical. This total state for the photon pair is a pure state, being the tensor product of the state for photon 1, 1 over square root of 2 horizontal plus vertical for photon 1 in this case, and the state for photon 2, 1 over square root of 2 horizontal plus vertical for photon 2 in this case. The source clock hits the designated time. One photon pair is generated on demand. Photon 1 travels to Alice. Photon 2 travels to Bob. Photon 1 arrives at Alice at the prearranged time. Her detector measures her photon's polarization and reports to her what? Her detector will report either that the photon is horizontally polarized or the photon is vertically polarized. It will never report that the photon is both horizontally and vertically polarized. The detection collapses the state of photon 1, but photon 1 has been absorbed, so that collapse isn't particularly significant. If we rerun this experiment many times with the same source state, we will find that the probabilities for reporting horizontal versus vertical polarizations will be equal, or will tend to be equal for a very large number of runs for this source state. The situation is comparable for Bob. Photon 2 arrives at Bob at the prearranged time. His detector measures his photon's polarization, and it will report either that the photon is horizontally polarized or the photon is vertically polarized. It will never report that the photon is both horizontally and vertically polarized. His detection collapses the state of photon 2, but photon 2 got absorbed. If we rerun this experiment many times with the same source state, we will find that the probabilities for reporting horizontal versus vertical polarizations will tend toward being equal, 50% for this source state. For this pure state of the source pair of photons, it turns out that Alice and Bob's measurements, detections, will be independent of one another. They are uncorrelated. Measuring and collapsing the state of photon 1 has no impact on photon 2's state in this pure state. If we do many runs with the same source pair state, when Alice's detector reports a horizontal polarization, half the times Bob's detector reports a horizontal polarization and half the times a vertical polarization. The two detections together are equally likely to report horizontal horizontal, horizontal vertical, vertical horizontal, or vertical vertical for this source state. This is a possible time to take a break. For our third experiment, we change the source to generate a pair of photons in the following entangled state. This is an entangled state, not a pure state. It is the sum of two tensor product terms and can't be re-expressed as a single tensor product term. One of the tensor product terms is horizontal for photon 1 and horizontal for photon 2. and the other term is vertical for photon 1 and vertical for photon 2. So shorthand, 1 over square root of 2 HH plus VV, where each of these is a tensor product term, and we cannot express this as a pure state. You should assure yourself that this is an entangled state. It cannot be expressed as a single tensor product. It is surprising that two photons can be created or prepared in an entangled state and travel away from one another, but they can. This is readily done and has very surprising consequences. The source clock hits the designated time, one photon pair is generated on demand, photon 1 travels to Alice, photon 2 travels to Bob. Photon 1 arrives at Alice at the prearranged time. Her detector measures her photon's polarization, and it will report either that the photon is horizontally polarized or the photon is vertically polarized. It will never report that the photon is both horizontally and vertically polarized. For any photon in this state, the probabilities for reporting horizontal versus vertical polarization are equal, 50%, for this source state. This is a possible time to take a break. Say that Alice's detector reports that the photon was horizontally polarized. The detection or measurement collapses the quantum state of photon 1, but something surprising happens here. The states of photon 1 and photon 2 were entangled by the source generation. Collapsing the state of photon 1 collapses the total entangled state, collapsing the state of photon 2. At the instant the detector measured that photon 1 was horizontally polarized, the total state collapsed from its entangled state, 1 over square root of 2 HH plus VV. It collapsed to state HH, which is now a pure state. Now when Bob measures his photon 2, his detector will definitely report horizontal polarization with 100% probability. Recall that we arranged it that Alice always measures slightly before Bob. Bob's detections are now completely correlated with Alice's detections. If Alice detects H, Bob will detect H. If Alice detects V, Bob will detect V, with 100% correlation. It is surprising that Alice's detection changes what Bob will detect, but this is the nature of entangled states, and it has been verified many, many times and never contradicted. Even more shockingly, this state collapse occurs instantaneously as far as physics can determine. No delay has ever been found. Information about Alice's detection is not traveling to Bob's photon or Bob's detector at the speed of light. It always seems to be instantaneous. Many experiments have shown that speed of light communication of the result was not possible in that experiment, nor does it seem to be a communication at a little faster than light. It appears to be instantaneous over kilometers of distance. This does not actually violate the special theory of relativity because no prior known information can be communicated by the state collapse. Alice cannot know whether her detection will produce H or V. It does not violate special theory of relativity, although it's weird and unusual, surprising, or shocking. The surprising nature of instantaneous collapse of an entangled state of two particles separated by kilometers has two fields of ramification. The first is testing the nature of physical quantum mechanical reality, and we will explore this in the next sections. The second is that uniquely quantum mechanical technologies are possible based on entanglement. We won't explore these as each such technology requires a good course of its own, and good free courses are available on the web, which I will list in the final section of this video. But just as an example, a stream of entangled photons of known total state will allow Alice and Bob to each know the other's detected photon states, and so they'll be able to share a secret key of digital bits. This leads to quantum encryption, quantum communication, and also quantum teleportation, the ability to teleport a quantum state of a particle from one location to a distant location. Doing this destroys the state of the original particle, so it is not cloning. And these technologies are also related to quantum computing. This is a possible time to take a break. Let's look at the state-of-the-art of entanglement as of this lecture. Quantum state entanglement of two particles that are separated, not bound together. It's not restricted to two photons. Electrons and atoms can have their spins entangled, as can certain defects in crystals. Photons can be entangled with atoms. Here are some examples of the state-of-the-art of entanglement as of 2020. Transmission of entangled photons via free space over about 100 kilometers of distance. Using entangled photons for quantum key distribution that has been accomplished at 1 million bits per second over 20 kilometers of fiber, 12.7 kilobits per second over 300 kilometers of fiber, and it's been accomplished between a ground transmitter and a moving aircraft over a few kilometers. 1,200 kilometers, 750 miles distance between two detectors on the ground in China, with the entangled photons beamed from a low Earth orbit satellite in 2017. They achieved 1 pair per second of transmission. The transmission of a photon entangled with an ion down 50 kilometers of fiber. Transmission of a photon entangled with an atom down 20 kilometers of fiber. Quantum correlated pairs of one visible and one infrared photon. Transmission of simple quantum states but not yet entangled photons from a geosynchronous satellite to an Earth ground station, a distance of 38,000 kilometers. And obviously, physicists would like to get to a point where they can transmit entangled photons to and from geosynchronous satellites. Quantum entanglement of billions of atoms, not entangled all with one another, but entangled in pairs and other combinations. Quantum entanglement of 15 trillion atoms in a hot gas. The entanglement remains for a millisecond, even though atoms are colliding in that millisecond. Entanglement between photons and bacteria. Testing for quantum entanglement in chemical reactions, such as photosynthesis. Quantum entanglement between billions of electrons in a special metal. A camera that records an image only of single photons and their entangled twins. Possible quantum entangled states inside a proton. Quantum teleportation of state between two chips, two integrated circuits. Quantum mechanics allows two distant systems to become entangled without contact by collecting photons emitted by both systems and entangling those photons together. This causes the two distant systems to become entangled. It is possible to entangle the state of more than two particles, but we will not cover this. We need to think of the quantum state of the system, not of the individual particles. If this step seems uncomfortable, it is. Quantum reality is complicated and weird. This is a possible time to take a break. The Einstein-Podolsky-Rosen EPR paradox and local realism. Beginning with the probabilistic Copenhagen interpretation of quantum mechanics, Albert Einstein was a thoughtful, incisive critic of a probabilistic interpretation for quantum mechanics versus an as yet unknown underlying deterministic reality. Typically, Niels Bohr was able to think deeply about Einstein's criticisms and explain how we should understand quantum mechanics, which has become accepted doctrine. In 1935, 9 years after Schrödinger's equation was published, Einstein understood the paradox of a measurement's instantaneous collapse of a wave function of an entangled state between two matter particles, described by position and momentum. Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper, now known as EPR or the EPR paradox. Can quantum mechanical description of physical reality be considered complete? The paper, written by Podolsky, did not completely represent Einstein's thoughts, and he published another paper in 1936. EPR used an argument concerning measurements of position and momentum of two distant particles with entangled states to conclude that the quantum mechanical description of physical reality given by wave functions is not complete, not a complete description of reality. To reach this conclusion, they declared that a reasonable definition of reality could not be expected to permit the reality of measurements on particle 2 to depend on the process of measurements on particle 1 long after the two particles had ceased to interact. That is, the particles' states initially interacted and became entangled, and then the particles separated and became isolated from one another. Yet the states remained entangled for measurements. EPR states that no reasonable definition of reality can be expected to permit this situation of the distant measurements being dependent. However, making the statement does not make it true. EPR believed that it would be possible to find a theory different from quantum mechanics that would explain the results of measurements of position and momentum on entangled separated particles without the instantaneous, spooky action at a distance of quantum mechanical state collapse of an entangled system. Einstein felt that the choice of measurement made on particle 1 could not affect the real state of distant particle 2, and so the quantum entangled state of particle 2 could not be its real complete state. Later, this would be conceived as the initial entanglement interaction creating needed local hidden variables, which then would be transmitted with each particle, sufficient for local measurement of any property of that particle independent of the other particle. This conception would be called local realism. The ensemble of the particle's properties, including hidden properties, is that particle's physical reality. The hidden variables were assumed to be sufficient to produce the appropriate result for any real measurement that could be done on the entangled system. Niels Bohr published a response to EPR in terms of complementarity of measurements. For example, measuring position is complementary to measuring momentum. But for decades, EPR stood firm as questioning the completeness and reality of quantum mechanics. However, physicists practitioners of quantum mechanics ignored EPR and pressed forward to successfully continue to solve problem after problem in physics and chemistry. Neither did any physicist discover a hidden variable, local realism, deterministic theory to supplant or supplement quantum mechanics, except for David Bohm's pilot wave theory, but this is not generally accepted. But EPR was left as an open question in physics, and in fact it was assumed that it would remain open forever until a better theory than quantum mechanics was discovered. This is a possible time to take a break. Bell's inequalities and quantum non-locality. In 1964, physicist John Bell published a paper proposing that spin measurements could be made in 3 dimensions on ensembles of pairs of spin-entangled particles in Bell states that we introduced in Lecture D5. Bell identified his Bell's inequalities that could be used to experimentally test whether measurements on large ensembles of entangled states could be explained by a general hidden variable theory of local realism, or could not, but would be successfully explained by quantum mechanics. I'm not going to describe his paper and his conclusions. That information is available in other courses and papers. But after his work was extended, all subsequent experiments were consistent with the quantum non-locality of quantum mechanics and inconsistent with hidden variable theories and local realism. You will see, if you read a book on quantum mechanics, you will see this reported as fact, as truth. However, physicists identified some loopholes in the experiments such that certain cases of hidden variable theories were not completely excluded and might still be a possible complete description of reality with local realism. Experimental improvements in quantum optics in the 2000s finally led experimental physicist Alain Aspect to publish in 2015 Closing the Door on Einstein and Bohr's Quantum Debate, writing, "By closing 2 loopholes at once, 3 experimental tests of Bell's inequalities removed the last doubts that we should renounce local realism. They also open the door to new quantum information technologies." So it is now accepted that as odd as quantum entanglement and state collapse are, they are reality in our universe. Bell's inequalities and quantum non-locality were again re-verified with entangled photons separated by 1,200 kilometers beamed from a Chinese satellite in 2017. Quantum non-locality is an important property of the universe and physical reality that is independent of our description of nature, and it leads to modern technologies, modern quantum technologies. Physicists want to learn how far we can separate particles and still have their states entangled. Can we have one particle on Earth and the other on a satellite in geosynchronous orbit? Can the other particle be on the Moon or on Mars? Can it be on an interstellar spaceship heading to another star? This is a possible time to take a break. Modern quantum technologies. Modern quantum technologies are well covered in many online courses, better than we can do in these brief introductory lectures. I would not be doing you a service to try to describe any of them when you can find free courses that will do a great job. It won't serve you for me to do a mediocre job and confuse you and lead you to doubt. There are courses in quantum computing and quantum internet, both in the same course. There are courses in quantum computing without quantum internet, courses in qubits, quantum bits. I have not found a course for quantum simulation of physical and quantum mechanical and chemical systems, for example, molecules, or quantum simulation of Hamiltonians. This is an important area in science and may be the best first use of quantum computers, but I have not found a course on that. Courses in quantum information science, quantum communication and quantum internet, but not quantum computing. There was a course that combined them. Quantum cryptography and quantum key distribution, quantum encryption. I have not found a course on quantum teleportation, but at least one of the courses in quantum encryption also covers that, or quantum internet. Quantum teleportation can be used for quantum communication repeaters, which are needed in a quantum internet. Quantum machine learning and AI. Quantum compass navigation might be possible in the future. Quantum radar might be possible in the future. In electronics, there are quantum dots, and this is a little different because it doesn't require entanglement. And I think there is a course in quantum dots, but I wasn't able to find it. Quantum transport in electronics. Quantum materials and topological insulators. Spintronics is a new important area in electronics, but I didn't find a course for it. There are some liquids are quantum liquids. There are courses in quantum optics. Tunneling is an important quantum mechanical phenomena in electronics, but would not be considered a new modern quantum technology. This is the end of lecture D6.